Let's start the second lecture by Johan. Please.
Thank you. So, by the way, if you wonder why I'm wearing a mask sometimes, it's not only because I want to blend into the Asian environment. It's also because my wife has a serious sickness, so she needs me to be helped. So I'm trying to just stay away from as many germs as I can, which might be carried by you, so please excuse me. Okay, so complete simulation of collider events. This is a very simplified picture of a collider event. We have a number of different stages in how to perform simulation of something like this. First, we have the high Q-squared scattering. So that's, you could call it the core of the simulation. What happens in the center there. So you have two high energy photons, two gluons in this case, colliding, and out comes some particles. So this is where new physics will appear, obviously. This part is process dependent. It can be described using first principles, and you can systematically improve the description if it turns out that you need better precision using higher orders, so extra loops and so on in your computation. The second part of the simulation is parton shower. So once these final stage particles here go out from your matrix element, there's a second stage, which is the parton shower, whereas where these particles split, so QCD particles split and radiate gluons and quarks. So this is all QCD, so it's all known physics, no new physics here. It's universal and process independent. So this is a very good point, that the whole process dependence is in the central part, the high Q-squared scattering. This is a first principles description, so we can use QCD, the theory of QCD, to give this description, and I will talk more about this, and also Grigory will talk much more about this in later lectures. Right. Then we have the next step. Once the parton shower is done, these partons somehow go from being QCD charged states of quarks and gluons into being color neutral states, so hadrons. So this is called hadronization, and this is low Q-squared physics, so this happens only at the end of parton shower evolution at a scale of maybe 1 GeV or so. It's once again universal and process independent, so it doesn't know what happens down here. And this cannot be described by first principles. So you need to come up with some models for how to go from your quarks and gluons to hadrons. And the reason for this is that we don't know how QCD confinement works. Finally, you have the lower part of this picture, which is the so-called underlying event. And this is due to scattering of other quarks or gluons in the same protons that were giving you your hard scattering. So the probability to have two high energy scatterings from the same proton is very small. So this is in general very low Q-squared physics. This is process dependent because it's dependent on the energy of the high Q-squared scattering. And there are a number of models for how to simulate this that are different. So it's a model dependent description.
Excuse me.
Yes.
Yeah, so here about underlying that.
Yeah.
And, I mean, so could you explain how do you know a priori that there's some process is process dependent and some process?
You don't know a priori. So in the original attempts at simulating this, they did not include any dependence on the energy of the hot scattering, and the description is not as good as if you include. So, I mean, this cannot be calculated from first principles, so you actually don't know. It's a model-dependent statement to say that it's energy and process dependent. I think it's clear from looking at what the actual events look like in the collider. You know that it's process dependent. When I say energy dependent, it's mainly talking about the energy of the collider. Of course, it depends very strongly on the energy of the collider. So actually, the models that were tuned to the teleptron turn out not to work at the LHC. You have to retune for the LHC. So the final step of your simulation is the simulation of the detector. So I've now shrunk this whole, everything we did up to now to a small point here in the center. And then we have particles coming out and being simulated in the detector. And of course, this is what the experimentalists spent a lot of time doing. They want as good detector simulation as possible. They leave this little thing here to us theorists. Okay, so a few words of different steps. High Q-squared scattering. How do we simulate this? Well, one way is to use Pythia. This is a list of the processes that are implemented in Pythia. It's a couple of hundred processes. They've all been implemented by hand, mainly by PhD students, because professors, to use a professor's time to do something like this, of course, is a waste of money. It's much higher salary than a student. You can say, so in principle, there are infinite number of processes that you might want to simulate for innumerable number of models. Of course, there are all the models that we haven't come up with yet, as well as all the models that we have come up with, but nobody sat down and implemented this scattering. So to do an implementation by hand, it's very time-consuming. It's typically a half-year project for a PhD student. So it's very labor-intensive, and it's very error-prone. Actually, there are examples of processes in Pythia, important processes, which, so the experiments had the wrong cross-section by 30% or so, because there was a sign error in the Pythia implementation. And, I mean, it just happens. It's not, you can't really blame anyone. It's just, it will always happen if you do this by hand. So this is a very bad use of PhD student time. So the better way to use PhD student time, which Tim Stelzer realized when he was a PhD student, is to write an automatized matrix element generator. And now we already did it, so you don't need to. Here you use the Feynman rules to automatically build the diagrams for the process and then calculate the matrix element. So this is a much better way of using PhD student time. The automatic matrix element generators that are around, these are the most important ones, I think. CalCap Complet has been around for many, many years, and it's very popular, especially among students, because you can turn on and off diagrams by hand in the user interface. MGraph has been around for many years as well. Talk more about that later. There's Sherpa, there's Wizard, and then there are some very fast and very efficient matrix element generators which only have standard models. So Alken, Alak, and so-called Conics, which is also part of the Sherpa generator. So, of course, we will talk about MGraph, because Olivier and I and Rickert are authors of MGraph. And that's also the name of the school. Next part is the Pottern shower. So, a very convenient fact about QCD is that matrix elements that involve splitting, so a Q to Q and a glue, or gluon to two gluons, splitting of this type, so here we have a quark, this is a gluon, are strongly enhanced when the final state particles are close in the phase space. So the matrix element goes like this. So we have a soft, sorry, I can't see what it is anymore. We have a soft divergence, so when the energy of the quark or the energy of the gluon becomes small. And then you have a collinear divergence when the theta between the two gets small. So what's really nice about the collinear divergence here is that the matrix element as well as the phase space factorizes, approximately factorizes, when you get very close, when you have collinear splitting. So the matrix element for the P plus 1 partons is approximately the matrix element for P partons times this new factor, which goes as 1 over T, where T is the virtuality or the invariant mass of the splitting particle. And then you have the Z, which is the Z is the momentum fraction taken by this particle. And then you have this function P here, which is a splitting function. And I will talk much more about this later, but the fact that this factorizes means that we can do step-by-step evolution, so the so-called Markov process. We can perform one emission separately, calculate the phase space for it, and then we can continue and do another emission, calculate the phase space for it, and so on, to have basically infinite number of emissions. This is called a Pottern shower. So there will be much more details about this in coming lectures. So Pottern shower event generators are very, very powerful. They have been used for about 30 years now in high-energy physics. They're general purpose, and they give a complete and exclusive description of the events. Exclusive meaning that in the end you have the full list of particles that come out of the event. So including the hot scattering, as you saw, there are several hundred processes implemented in Pythia, for example, showering, hadronization, and underlying events. They're very reliable, very well tuned to experimental data, since they've been around for so long. The most famous ones are Pythia, Herwig, and Sherpa. There has been intense progress in the development of new showering algorithms in the last few years, with the aim of going to next leading order in QCD in the Pottern showers. Next leading order in QCD in the matrix element will be talked about by Rickert later on. Finally, we have the detector simulation part. So for a theorist, the detector simulation that's mainly used is fast general-purpose detector simulators, such as DELTS, PGS, which stands for Pretty Good Simulations, or ACIDET, which is very, very old, but fast and sometimes good enough. So in these detector simulations, you can specify your parameters of the detectors to simulate different type of experiments, such as the LHC experiments or the Tevatron experiments. So these are very convenient. Then, of course, each experiment, the experimental groups, they have to give their own detector simulation. So you have fast experiment-specific simulation, where the response of the detector is parameterized according to some functions, and the runtime is typically between milliseconds and seconds for one event. Then you have the experiment-specific full simulation, which means that you take all the particles coming out of the hybridization simulation. And then you track exactly how these particles go through the detector and how they evolve using the GAN software package. And here we have a runtime of several minutes for one event. So when you're writing or using a matrix element simulator and all the other parts of the simulation, as long as you have runtimes which is below minutes for one event, unweighted event in the end, basically the main part of the simulation would be the detector simulation. So this is why people are doing next leading order calculations or next leading order simulation, because although it's extremely slow compared to leading order, it's still usually faster than the detector simulation. Okay, so any questions so far? Please ask questions.
Why do you need a detector simulation? Because you show the main diagram and you calculate the cross-section anyway.
Right.
And why do you need a detector simulation?
The reason is that, say for example that in your quantum level process you have a particle which decays into 2 jets. And the decay width of this particle is 1 MeV. You will have an extremely strong spike in your cross-section. When you now send this through a detector simulation, the detector has a finite granularity, so and not very good response, and you also get some smearing of the momentum. So in the end, this will change this peak, which was a spike, into something which is wide, maybe a few GeV wide. So it can change. The detector simulation can change your result by 1,000 easily. So if you're just interested in the process, but you don't care what it looks like at LHC, then you can work only with the quantum level. But if you care about how the experimentalist will be able to find your new model, for example, then you definitely want to run it through the whole chain with showering, hybridization, and detector simulation. So in general, this one is so easy to do. So now theorists that write papers are expected to also do this. Other questions?
If you know potential or hybridization bonus, the scattering is network.
Sorry?
In the process of potential or hybridization, the particle also can scatter. Multi-scattering.
So that's simulated by the underlying event. So actually, I can go back to this picture. Here, yeah. So the Potter shower takes whatever comes out of the matrix element and performs additional splittings and radiation of acoustic. So it's just like Ramshaw and Q. So it performs radiation of acoustic particles. But each event that you send into the Potter shower, you'll get exactly one event out. So you'll get exactly the same. You start with a number of particles, and in the end, it will be only those particles that are showered. It's this part down here, the multiple scattering, that is usually simulated as separately from the shower. So was this your question? So there's no scattering in this. It's just radiation. There's no scattering in the shower.
What is the virtuality of the final gluon for pop in the final state? virtuality. You mean you mentioned that in the pattern shower here is a term corresponding term to the virtuality of the mud particles.
Sorry, I can't hear you that well.
I mean the final particles generated from the MGraph or event generated. And its virtuality is the final particle is if the final particle is unchecked, then virtuality is 0.
Virtuality.
Yeah, but however, in your pattern shower program.
This is a very good question. Yes, good point. So actually, in the pattern shower, there we go. Yes. So the way it's done in the pattern shower is that you start by having this on shell, but you know that you have a certain energy. This particle has a certain energy coming out, so you know that it should be radiating because it has been strongly accelerated. So what you do is, in your matrix element calculation, you treat it as on shell. And then you perform the splitting, starting from, I'll talk much more about this tomorrow, but starting from the energy that you have here. And then you change the kinematics of this whole system in such a way to accommodate for the virtuality that has been given here. And then, same thing next step. These two are considered on shell. And then you will continue and do more branchings and continue to revise your kinematics up here. This is a very good point. And the reason it works is that the enhancement is for very small energies and very small angles. So each successive radiation has much smaller energy and much smaller angle than the previous one. So from the point of view of this final state, this is approximately on shell, because the next radiation will be so small that this can be considered on shell to good approximation. So this is the way this is motivated. In practice, of course, it happens that the radiation is actually pretty hard, and you need to do a pretty big change in the kinematics of the original. So exactly how this is done depends on your pattern shower program, and there's no theory for how to do it. It's just different ideas, and it's just used different ways. And then you can compare to experiment and see that this works better, this doesn't work as well. So that part is not from first principles. Very good question. Thanks. Any more questions? Okay, so I have been going through matrix elements on one hand and pattern showers on the other hand. Of course, when we look at an event here, let's see, it's not obvious what should be a part of the matrix element and what should be a part of the pattern shower. So this gluon coming out here, for example, maybe it could have been generated by the pattern shower instead of the matrix element. So why does it come out from the matrix element here, in this red blob here, instead of being generated by the pattern shower? So in fact, these two descriptions, of course you can describe gluon radiation using matrix elements, or you can do it using pattern shower. So these two descriptions are actually kind of complementary. So the matrix element it's a fixed order calculation. So you can do it at leading order, next leading order, etc. And it's very computationally expensive because you need to do this phase space integration with whatever final state that you choose to have. So this means that you can only do for a limited number of particles. In practice, well, you also have the matrix element itself, which very quickly gets complicated, especially in QC. So in practice, you might not be able to simulate more than maybe 4 final state partner spores or gluons. matrix element is valid whenever the partons are hard, meaning have a large momentum, and are well separated. So whenever they get close in phase space, so whenever you get a small angle, or you have very soft, so very low energy of the partons, actually the matrix element description is not valid, and you need to do resummation of a matrix element. You get quantum interference completely correct, and if you want to get a good description of multi-jet production, so multiple jets which are hard, have high momentum, and are well separated, and a collider, this is the description that you need to use. On the other hand, a shower-mounted column has other advantages. So it resounds to large logarithms, which I think I will talk about a little bit tomorrow. I'm sure that Gregory will talk a lot more about the summation of large logarithms. It's computationally very cheap because you just do one splitting, you just have a very minimal phase space of 2 particles, then you do another splitting, still a minimal phase space of 2 particles, etc. There's no limit on particle multiplicity. You can up with 1,000 partons by doing this stepwise splitting. But it's really only valid when partons are collinear or soft, because it's only in this region that the factorization idea works. You can get some partial interference through something called angular ordering, which probably you will talk about a lot too, because it's something very important for the partnership. And as I said, at the end of the day, what you want in the end is hadrons, because what you see in the detector is hadrons. And it's the parton shower which allows you to go from the hard process, the matrix element, and out to the point where you can do hadronization. So shower Monte Carlos are absolutely crucial. Matrix elements are also absolutely crucial. So what do you do? Well, these approaches are complementary, so we need to merge them. And there are a few difficulties when doing this merging. One is to avoid double counting between the two, because, as I said, gluon can be simulated using the matrix element, but it can also be generated by the shower Monte Carlo. And then you need to ensure smooth distributions. It shouldn't matter exactly how you do this merging. You should still get the same description. So just to give you some teaser, when you run the parton shower by itself, as I said, parton showers can be tuned, so you can choose different parameters for the parton showers and see what best matches the data. So you can get very different descriptions. This is, here you have decades, so 10, 1, to -1, etc. This is the GV, in GV, the PT of the second extra jet in TT bar production. And this is the curve for the PT of the second extra jet, depending on different choices for your parton shower. So you have 4 different parameter choices for the parton shower. And you can see here that pretty quickly you end up with a difference between the hardest choice and the softest choice, which can be several orders of magnitude. So basically the parton shower, it's very good because you can tune this to actually fit your data, so that's nice. On the other hand, you have no predictive power at all. I mean, you can have basically any of these curves. When you now use the matrix element instead, all these curves fall together into only one. So this curve here is given by the matrix element. You still have the same variations in the shower treatment afterwards, and I will talk much more about this tomorrow. But we see that our description becomes basically unique. These variations are only due to statistics. So once you apply matrix elements and do this matching, you get a completely predictive description. So actually here you know that QCD should work this way. You should get this result from the result. So the way that this can be done, the very quick and simple explanation of how to do this. So this shows you the problem that you have. this is your matrix element, and then you can apply Poisson showers to the matrix element. On the other hand, you can have extra radiation in the matrix element, and you can apply Poisson showers to the extra radiation, etc. So we see that we'll naturally get double counting between emissions that are done calculated with the matrix element, and then events like this, which are where you apply Poisson showers, and the Poisson shower produces exactly the same extra gluon that you have in this matrix element. So this means that you double count these events. You should only have one of them. So how do we take care of this? Actually, it's very easy. We just apply some phase space cut, you can call it KT, and say that if this KT is smaller than QC, some cutoff scale, then we allow this to be Poisson shower. If it's larger, then we call it matrix element. So here we see that the Poisson shower, we always keep it below this cutoff. The matrix element, we always keep it above the cutoff. This way, there is no double counting, and we'll for sure simulate the same type of events only once. So these resulting events will then be exclusive, meaning that you can, once you have done this, you can add up all these different matrix element samples with the Poisson showers, and you will get a complete description of, in this case, gauge boson production plus jets. So what's still to be explained, and what I will spend a lot of time on tomorrow, is how to make sure that the distributions are smooth, and make sure that it doesn't depend, the distributions don't depend on exactly how you do the merging, where you put this cutoff. So this is a nice little picture from one of our competitors. I want to include it only because maybe one of the competitors will look at a video that will be on the web, and then they will be happy because they see there's a picture from them. So anyway, this shows the distribution of the PT, the transfer momentum of the C boson at the telectron. This is CDF data. And you see that you have a very nice description of the CDF data. In fact, this looks very simple, but it's very complicated because you have no less than 4 different jet multiplicities which are added together after doing this procedure. So we have the 0 jet here, we have the 1 jet, the green one, 2 jet, and 3 jet multiplicities, which are added together to give this black curve. And as you can see, the black curve very nicely reproduces experiment. The cross-section, you need to scale the whole curve up, and that's due to next feeding order effects that we could look at.
I have a question. Yes. How can you determine the scale of the cutoff?
So as I said, you need to be very careful with your treatment to make sure that the distributions are smooth. If the distributions are smooth, then the exact point of the cutoff should not be important. You should be able to change the cutoff up or down a little bit. You still do need, you can't put it anywhere. For example, if this is a W boson, if you put the cutoff above the mass of the W, then for sure you will not get a good description. The reason is that the Poisson shower, you need to put the cutoff where the Poisson shower description is still valid. If you put it too high, then you know that you have hard jets and the Poisson shower is not a good description. You can also not put it too low. If you put it extremely low, then the matrix element description will be so bad that even if you do everything you can to improve the matrix element description, you will have this very large number, and then you need to apply a very large weight to this to get it down to the correct description, and you probably won't be able to do it correctly. So if you want to choose this in an intermediate region, I'll talk more about this tomorrow, but typically in MGraph you usually want to use maybe your hard scale, so the W mass in this case divided by 6 up to maybe W mass divided by 3. So
you mean that the result, the cross-section, depends on the KT. But
so
you can optimize it.
So the cross-section should not depend on the exact value of the QC, but you need to choose it in an appropriate region. So if you vary for, say, W production, if you vary from 10 GeV to 30 GeV, it shouldn't make any difference. But if you go down to 5 GeV, then probably you won't be able to do it. If you go up to 100 GeV, for sure you will not get a good description. So you need to keep it within a region, a good region, but you can vary it within that region. Sorry. It's very easy. You look at the plots. If your plots are smooth and you vary your cut and the plots don't vary too much, then you're okay. Guidelines, but not exact ones. Any other questions? Okay. So what I wanted to do now is to give you an actual demonstration, real-time demonstration on my computer of how to do event simulation with MGraph in practice. So this is very dangerous, so everybody cross their fingers, because usually when you try to do something in real time, you will always fail, something will go wrong. So how to do event simulation with MGraph? Well, the easiest way is, if you have an automatic computer, you can edit it yourself. The easiest way is to go onto the web. You can just Google for MGraph and you click on the first hit. You register if you haven't done it already. I think you all registered already. You type in your process. That's what it's doing here. You press submit. And then you can either download the tar file that you get or generate events directly online on our clusters. So in principle, you can use, if you have an account and you're allowed to generate events directly online, you can use your iPhone to do it. I don't have an iPhone, I have a Sony Ericsson, but it's on Swedish. Sony is, Ericsson is Swedish. You're Japanese, so you probably also have a Sony Ericsson. So that's the really easy way to do it. But here we want to be a little more advanced. So instead, we'll use MGraph on our own computers. So what you do, I think you've all done this already. You downloaded MGraph 5. You check that it starts and so on. Good. You untar the downloaded package. You run bin/mg5. You write generate and then your process. You write output and you write launch. So not so much more complicated. So let's see. Very good. So I have performed the steps. I downloaded MGraph 5 version. This is actually one version older than the latest. The changes in the latest version do not affect this. I start in MGraph 5. Actually, I also run the install command, like I think you've done. So I have map analysis. I have FlexPGS. Yes, those. So you run bin mg5. So how far down can you see if I pull this down? Just say one. Whoever can't see, just sit. Right? This is good? Okay. So as you can see, it's already loaded the default model, the standard model. It's performed something which is called restrictions, which I think Benjamin will spend one slide on. Thank you so much for that. This is very important and very nice, but I won't talk more about it now. And it's also defined, for your convenience, it has defined some multi-particles already. So proton means this collection of quarks and gluon. Jet, same thing. Then you have lepton, lepton plus, lepton minus, and lepton neutrino. So now, of course, rate, here we go. Generate PP goes to TT bar. Let's do this. Very simple process. we can edit our cards. So there's a param card we can edit. The param card, it might look complicated, but it's very easy because you can see here what is the actual variable that's being modified. So the mass block has these different masses. Note that, actually, we should write it already here, a warning. If you change the top mass, for example, then you need to also change the top width accordingly. So in general, don't change this parameter part. But we can look a little bit at it. So as the masses, as some standard model inputs, Yukawa, and decay width. Then we have the run card. And this is also very clear and easy to read because there are a lot of comments in it. So we have a number of events. Let's remove 1, 0 just to have a very quick run. MGraph is very fast, but PGS is very slow. Since I was running PGS, I just do 1,000 events. You can choose the collider type and the collider energy. So this is where you determine between LHC and teratron. 1 is the proton, -1 is the antiproton. So this is LHC 14 TeV. He also put down your renormalization and factorization scale if you want to use fixed or dynamic scale. So if you use an event by event scale, you will in general always get a reasonable result. So I always do that, since I implemented the scales. You also have a bunch of cuts that you can choose. Here you have the PT of jets, PT of B, PT of leptons, minimal and also maximum cuts. You have eta cuts, and you have delta R cuts. Since we're producing tops, so we don't need to care about any of these cuts. Cuts are mainly for light. Of course, we want to have that. Okay, so now we modified our run card, and then filter card we can just use the default, PGS card we can use the default. And now, lo and behold, it opens a web page in the browser, and here it actually says that it's running already. So we can check, yes, indeed, it's running. So let's take a look at the process. I clicked on main page and click on process information. Well, we see already here that it's PP goes to TD bar. This is an example of a final diagram to give you an idea of the process we're working with. And if we click on the process information, we see that we have 2 sub-process directories. One is glue goes to TD bar, and one is quark, anti-quark annihilation. We can click on the diagrams. So we have 3 diagrams for glue goes to TD bar. And how many diagrams would you guess? Now we have the answer here. Like this, okay. How many diagrams would you expect to get for quark anti-quark TD bar? Anybody? Anybody very young who wants to make a guess? Well, you can see that it's 1, but is that really what you would expect? 3. Very good guess. Which are the 3 diagrams? No, that's not the reason for a good guess. In glue to TD bar you have these 3 diagrams. But in QQ bar to TD bar you only have the S channel. So you only have this diagram. But you would expect also to have a diagram with a photon in between, right? Because we have the standard model, so a photon or a Z. But they're not there. So why are they not there? The reason is that you didn't specify that you really want these diagrams. These are completely subdominant, so we assume that you only want the dominant, the most important contribution. So when you just ask for PP goes to TD bar, you will only get the dominant contribution, which is from the gluon exchange. So now, the run is of course already done, because we wrote the program and it's very fast. So you can see here, this is the cross-section, 556 picobond. Those of you who are very good at LHC physics know that the cross-section should be 800. And the reason for this is that 800 is the next to leading order number, which is typically a factor 1.5 or so higher than the leading order number.
You said that the photon process and Z-boson process can be neglected because the subdominant.
Yes.
If you consider some process which the Z-boson or photon process is dominant,
yes.
Should I need to specify the process?
No. We always know. And the reason we know is that the model builder, in this case, Vendela, has specified what is dominant. So we always know. So you don't need to worry about it in general. Unless you want something which is different from what you would expect. So you can click on results, and here you'll see that indeed, I told you in the beginning of the last lecture, if you have very good memory, you might remember that at the LHC, blue is dominating over QQ bar. And you indeed see that blue has the dominant contribution. QQ bar has much smaller. You can also see that we have generated plots. So plots at bottom level here. So in principle, all you need to do now is collect these plots and you upload your paper on the archive. Very convenient. This case shows the PT of the top, the anti-top, the rapidity distributions, and the invariant mass of the top and the top. Now we also have plots after Pythia and after PGS. So after Pythia we have a huge number of jets here. Why do we have a lot of jets after Pythia? In the bottom level distribution, bottom level plots we have no jets. Why do we have jets after Pythia? Tops decay into jets and leptons. So you get a lot of jets from the decay of the top. And as you can see, most events have about 4 jets. And this corresponds to the largest decay mode of the TQR, which is semi-leptonic. So one top decays to hadrons, one top decays to leptons. You have Bs. You have, in general, 2 Bs in each event because the top decays, actually the jets is the Bs and jets. And then you have electrons and muons who come from the top decay. And then you can look at things like the PT of the jets and so on. Then you can compare this with the result after PGS. So PGS is the detector simulation. And then you see that after PGS you actually have a little bit different number of jets. You have a different number of Bs. So you see that PGS is not that good at recognizing if a jet is a B jet or not. You have electrons, muons, and so on. So actually, you have everything in from just this page. You have photons.
I have a question.
Yes.
So already at PPL level, the number of B is not really about 2. So it means that at PPL level, we already have some efficiency.
Actually, the reason is that at PPL level, the way that these plots are from a very crude program which just assembles the PTA events to give something that you can look at. And there, I consider a jet to be a B jet if a B quark from the bottom level goes in the same direction as the jet. So sometimes the jet is shifted compared to the B quark and then it won't catch. So there's no deep physical meaning of this. It's just that sometimes the B's are going in a slightly different direction. Okay, so I said that the QED diagrams or the Z and photon diagrams are subdominant. I can actually prove it by running the same simulation, including the QED diagrams. This I do by setting QED equal 2 after my process. And this means that we ask for 2 QED, maximum 2 QED vertices, but we also allow as many QCD vertices as we want. So it's not exactly 2, it just means we allow up to 2 QD vertices. So do the same thing, output, and launch. We don't need to run Pythia this time. We don't need to edit the path card. We can still run with 1,000 events. And here, if we click on the main page, here we see that indeed we have 3 diagrams for QQ bar. So it's the photon, the gluon, and the Z. And we also see that the process, before we only had one process for QQ bar. Here we have split it up into 2 processes, one for UU bar to QQ bar, and one for DD bar to QQ bar. What would this be? It's because U quarks and D quarks couple differently to the photon and Z. So actually these are 2 different matrix elements, different temperatures. When we have just QCD, then all the quarks are the same. So now if we go back to our results page, it's already done. Let me just clean up a little bit. So we can compare the cross-section, and we see that the cross-section looks very, very similar. If we look a little more carefully at the results here, we see that the cross-section for the gluon is exactly the same, of course, because there was no difference. The cross-section for the QQ bar, where we actually have these extra diagrams, changes in the 3rd integer. So we have a very, very small contribution from the photon and Z, but it's completely negligible, as I told you. So everything is good. So for the last 5 minutes, maybe it will take 10 minutes, I hope that's okay for you. I would like to do a considerably more complicated process. PP goes to W plus jet, and then the W decaying into lepton plus and lepton minus. Now this is a really complicated process. 178 different diagrams or so. We do output. It does a lot of work, and imagine the amount of work that you would have to do this by hand. So this guy does it in about 1 second, actually 2 seconds. And then we do, launch. Let's run Pythia. Let's not run PGS. We don't need to edit the power card. Let's use the standard counts. Remember, it was 20 GeV jet count and 0.4 and delta R for the jets. And we keep the standard Pythia card. Okay, so now we can start checking what this process looks like. So you can already tell from this preview diagram here that it's a kind of complicated process. You have, let's see, 1, 2, 3, 4 main subprocess directories. So this is glue, glue Q goes to glue Q, QQ goes to glue. So this is QQ and QQ. Actually, this is QQ bar. And here we have QQ goes to W plus and QQ. So QQ bar, quarks and anti-quarks. And as you can see here, so we can start by looking at the diagrams for this. It's simple enough, 8 of them, so not too bad. Maybe we can do it by hand. This one, I'm sure actually Cora did this at some point. He is one. So here we only have one subprocess. And the reason is that DU bar and SC bar couple in the same way to the W plus. So here we only need one subprocess. However, when we have group Q to W plus to Q, we actually need 2 subprocesses because we treat initial state quarks and initial state anti-quarks differently. This is for this, but we reverse the order of the quark-handling gluons. And then we have this huge, gigantic process library here, which actually contains, what is this, 15 or so different matrix elements. So the reason that these are different matrix elements, so they have different diagrams. This guy has 4 diagrams. These 4. This guy has only 2 diagrams, for example. So these are all different, matrix elements, but they're all put together into one subprocess directory. And the reason is that the types of divergence structures that you can get when you have 2 quarks incoming and 2 quarks outgoing are the same. So some of these diagrams show up in the same way. So say this diagram, for example. Look at this and remember it carefully. And then I think this one should have it. Yeah. The diagram looks exactly the same. So we can use the same integration channel to integrate these 2 different subprocesses together as just one subprocess. So I hope I've convinced you that this is not something you want to do by hand. Maybe you can, but you probably don't want to. So if we do this instead using MGraph, then of course everything is fine. So we actually already have some results. We have the cross section with an error of about 1%. We can already look at which subprocesses are dominant, which are subdominant. So we see that actually the glue quark fusion subprocess is completely dominant. And what's the reason for this? You tell me, why is this the dominant subprocess? Do you remember in the beginning of the first lecture, it's been almost 3 hours now, so it's a long time. I showed you the bottom density functions. You might remember that the gluon is extremely strong. It goes up extremely fast. In the picture, it looked like this. It went up faster than the quarks, and that was when it was divided by 10 already. So the gluon, for sure, has a very large luminosity. Then, you might also remember that the U quark had this kind of funny bulge, so it's very strong. The U quark is also very strong. But the U quark is strong for high X, the gluon is strong for low X. So what you get here is scattering of a U quark for high X and the gluon for low X, which gives you a very high, extremely high luminosity. Then the next strongest is QQ, or QQ bar goes to QQ bar. And that is partly because you have so many different subprocesses which are included together. And then you have QQ goes to glue, and then finally glue goes to W. So you can see that we've already finished using the 10,000 events that you asked for. So this is a very complicated process with a lot of sub-processes and everything, but we can still do it in about 5 minutes on this laptop. So we're pretty fast, actually. We can look at the processes, at the plots. We have 2 jets in each event. We have the same, you see here, this is 796, this is 792. So we have one, this is the cross section, not the number of events. So we have one positron and one positron in half of the events, one muon in half of the events. This shows H2 missing in T. The missing in T comes from the neutrino, of course. You have the PT of the first jet and the PT of the second jet. So you can see, I told you that in QCD, the jet distributions are very strongly peaked for low values for low momentum of the jets. That's what you can see here, that you have a very strong enhancement for low momentum. So you can actually learn a lot just from looking at these bottom level points. Then you have the PT of the positron and the PT of the muon, and this doesn't have the course, it doesn't continue up because they come from a W decay. The W has a mass of 80, so you should have a peak at around 40, which is what you can see. And then, let's see, anything else? Oh, that's the most interesting stuff. And now we're also done with the Pythia run. So we can compare the plots that we get from the bottom level and the plots that we get from Pythia. So the first thing we notice is that in Pythia we have many, many jets. So I told you in GT-bar, the reason we have many jets is that the top decays into jets. So why here do we have many jets? Anybody remember the beginning of this lecture? What happens when you run something through Pythia? Pythia is a bottom shower generator. Come on, guys. Yes, you have radiation from the jets, from the final state jets, but also you have radiation from the initial stages. Yes. So this extra radiation will generate more jets than you have in the matrix symptoms. So you always get more jets after Pythia. So this is another reason. Somebody over there was asking why you can't just look at the bottom level events, why you need to run through Pythia and detector simulation. This is another reason that actually if you generate this process and you think that, okay, so my process looks in the detector should look like a W and 2 jets. Well, in fact, after you run this through Pythia, it turns out that it looks like a W plus 3 jets. Because you have 3 jets in the majority of the times. Of course, this depends on where you put your jet covers. Then you actually have some B's, even with something else. The electrons and muons, though, they are still, you have the same number of electrons. Electrons in half-day events, muons in half-day. So that's good. Then we can start comparing other plots. So in particular, something very interesting to compare is the missing ET. So the missing ET, as I told you, comes from the neutrino. So you would not expect the showering to have a big effect, or hadronization to have a big effect on missing ET. And indeed, when you look at these plots, they look almost identical. The scales are different because this is in cross-section and this is in convolution. But otherwise, the plot is almost identical. So this shows you that if you have a lot of missing ET in your core process, you don't need to be too worried about the missing ET distribution when you go through Pythia. You still need to run detector simulation because that has a big effect on missing ET, but Pythia does not. Then you have the PT of the first jet, which is also it's pretty much the same, which is what you want, because you don't want Pythia to make a big change in the kinematics of the hottest jet. You know they will add additional jets, but it shouldn't make a big change in the kinematics of the hottest jet. Pythia of the second jet, here we have a bigger change because we have extra jets produced by Pythia, which are typically between the first and second jet. And so on. So you can keep looking at these plots and actually learn a lot of interesting things. And I would recommend for you to do that, but now I think we need to have lunch. So let's see. These are the examples that I showed. I just repeat them here. So when you go home and you look at the slides, you remember what I did. And here are some more examples of syntax. So as I told you, when you add an explicit number of couplings for some particular coupling, then we no longer take responsibility for giving you the dominant contribution. So then you'll get all combinations of the particles defined in these hot particle levels, including up to 2 QD levels, an unlimited number of QD levels. So in general, you don't want to specify the couplings because we know what is dominant. But if you do want to specify the couplings, remember that you'll get unlimited vertices in all other couplings. here is another example. I showed you already a decay chain, so a W decaying into lepton and neutrino. You can write much more complicated decay chains like this. So here we have TT bar production with a top decaying to BW, W decaying to L plus lepton and neutrino. And here we need a parenthesis because this W decay is from this sub-process. And then the T bar we just decay directly to T bar into J. So when we do a decay chain, you'll get only diagrams compatible with the given decay. Olivier will talk more about this. And this is also important. The T and the T bar and this W here will only be allowed to be close to the mass shell in the event generation. So you will not get T's and T bars which are extremely far off the nominal mass or pole mass. So how far off can be decided by a flag in the run card. You can do a forward dash like this and put the particle afterwards, and this means you exclude any diagrams with that type of particle. So as an intermediate set. So in this case, W plus W minus can come from the Higgs, but here we exclude the Higgs, so we won't get those diagrams at all. If you want these diagrams, you want the Higgs, but you just don't want the Higgs peak, because you're not interested in the W plus W minus from Higgs. You're interested in W plus W minus, but you still want the interference effects from the Higgs. Then you can use the dollar sign. So this would exclude on-shell Higgs in the event generation, where on-shell is defined in the same way as in the decay chain, but you will retain interference effects. So for the decay chains, Olivier will talk a lot more about this in the afternoon. He will not mention this. And why this is important, it's very important when you do certain types of processes, particular match processes in new physics models. But that's for the next school. Okay, so thank you very much for listening. And after the lunch, we will turn over to you.
Thank you very much. Any other question?
What if the solution of fluid is much smaller than the fluid for the W plus just production?
The reason is that you have. Let me actually show you that. So the W couples, as you can see from the diagrams here, the W couples only to quarks. So you will for sure need to have quarks in your process. You need to have a quark line. So whether the blue here. So here the quarks are only produced in the final state like this. So you only have gluon fusion.
The two-gluon distribution is much larger than the Q-PDF distribution. I think two-gluon.
So this is true, but it depends on where. Let me see. This is the one, yes. So it depends on which X. For large X out here, actually the up and down quark distributions are much larger than the gluon distribution. For small X, let's see, this is 0.1, this is 1. So yeah, for X up here, they are much larger. For smaller X, the gluon is much larger. So what you can do here is, in this process, is you can have a gluon, which is at very low X, fusing with a quark at very high X. When you multiply the X's, you get the S hat, so the numeric mass.
The moment fusion from the large momentum fraction.
The dominant contribution is
from the
large momentum So this is one reason. Another reason is that the matrix element is different. So, but this is the simple solution, simple explanation. We have this very strong enhancement of the quark luminosity for large X, and you can now pair a quark for large X with a gluon for very, very small X. We have an extreme enhancement in the gluon. If you need two gluons, you will have them both at more intermediate X. So you don't get this extreme enhancement.
Your photon beam includes gluon and up-down charm and flange as a pattern.
That's right.
Is it possible to include also the bottom form?
Absolutely. You just do a redefinition. It's not. You just do define P equal P bar like this, and then you have the two P's. So you can absolutely do it. But in this case, of course, it's not. So in this case, it's not relevant because the V, just as we also saw actually here, the V is so much smaller than this. But if you need the V in the initial state, you can definitely.
Usually the photon density, they are just the empirical data.
Sorry.
Photon density function
Yes.
is empirical data.
Yes, absolutely. I will talk much more about photon densities tomorrow.
So I don't see any more questions. So let's thank Johan again. So we have I think here is the lunch coupon for you, and lunch, the cafeteria is on the second floor of this building. Behind. So we all go together. We can go either by going outside this building and then off to this building, or we can go to the third floor and going down. I think going out is probably shorter.